In these slides, we will be talking about other model-based approaches to collaborative filtering besides matrix factorization. We have already talked about matrix factorization, and so we will continue with factorization machines, which can be considered as an extension. Then we will talk about another idea called the sparse linear method, before talking about approaches based on neural networks. Towards the end, we will revisit matrix factorization and discuss how it can be adapted for the case of implicit feedback. There, we will talk about two main approaches. We will discuss factorization machines and how they are related to matrix factorization. Factorization machines can be considered as an extension of matrix factorization techniques. They have the benefit that they can encode multiple attributes about users or items. That is, they can incorporate multiple sources of information besides the user-to-item feedback. Moreover, they can potentially capture higher degree dependencies between features. We will see this a bit later. To understand factorization machines, you need to think in terms of training examples and labels. In our case, a label is a rating of some item by some user. The training example contains information like the features that concern the rating. This information is the user ID, the item ID, as well as additional or side information about the user, item, or context of the rating. Let's see an example. In the figure here, we see a number of training examples and labels. Each row corresponds to a particular user-to-item rating. The label at the end is the rating. The sources of information in this figure are the user ID in blue, the movie ID in red, other movies the user has rated in orange, the timestamp of the rating in green, and the last movie the user rated in purple. Users and movies are one-hot encoded. This means that for encoding movies we have as many red columns as the number of movies. To indicate a particular movie, we put 1 in the column of that movie and zeros in all other movie columns. Similarly, to represent a set of movies, we set as 1 the columns corresponding to those movies. In the highlighted first row, we see that user A has rated movie TI, which stands for Titanic, with a rating of 5 stars. Moreover, the user has also watched the first 3 movies listed, TI, NH, and SW. The last movie rated is not shown here. Let's now discuss how to use the available information about a user item rating in order to predict the rating. Here's one training example, specifically represented as a vector of features or attributes denoted as XUI, and the rating is denoted as RUI. The goal is to use the XUI vector to predict the RUI value. So what is the first idea that comes into your mind? Okay, well, let's try to apply linear regression, where XUI contains all the available features. In basic linear regression, the prediction, that is the predicted rating, is a linear combination of the features. This is expressed by the formula shown here. The value of each column P is multiplied by some weight WP, and then all these weighted terms are summed. A biased term, mu, is also included. In our case here, the bias can be thought as a global average rating. So we have expressed the predicted rating as a linear combination of the features. The goal is then to learn the appropriate weights in the linear combination. This is the learning task. This was the simplest linear regression model you can describe. A slightly more complex modeling is to also include higher order terms. This means that in addition to the features attributes that we are given, we will be combining them to synthesize additional attributes. This is useful because that way we can express non-linear relationships between attributes. A simple example where higher order terms are useful is when we want to predict the price of a house. Suppose we have as features the area of the house in square meters and the average price per square meter of the neighborhood. A simple linear combination of these two attributes is not likely to be a good model. However, assume we create an additional attribute by multiplying the area with the price per square meter. Then this synthesized attribute would be much more predictive of the price. So we can apply this idea in our case. We create synthetic attributes by multiplying every possible pair of attributes. For each synthetic attribute, say for attributes P and P prime, we have a new weight, WP prime, that we need to learn. The predicted rating now consists of three terms. Mu is the bias and can be considered as a term of zero order. The linear combinations of given attributes is the second term. It captures interactions of attributes alone, hence interactions of first order. The last term is the new term capturing interactions between two given attributes, hence interactions of second order. If we want, we can include higher order interaction terms, for example by multiplying three attributes, but maybe this is too complex. For now, we consider the formula shown here. There is a problem with this higher order linear regression idea. Can you see it? It's hard to train such a model because there are too many weights to learn. So how many synthesized second order terms are there? Just consider the attributes about the users and the items. There are m blue columns and n red columns. Based on these columns alone, we can create around n plus m squared synthetic terms. This means that we require as many weights to learn. And this number of weights is even larger than the number of all possible ratings n times m. So clearly this will not work. So what can we do? And the solution is the main idea behind factorization machines. Consider all weights WP P prime and arrange them in a big weight matrix. And the idea is to factorize this weight matrix and express it using much fewer parameters. So instead of learning all weights in the matrix, we will be learning much fewer parameters that can help us reconstruct the matrix. The factorization works as follows. Each attribute P has a latent vector of some fixed dimensionality, say k. A weight for the interaction between attributes P and P prime is then expressed by the inner product between the latent vector of P and that of P prime. So this is the idea behind factorization machines. They allow us to use higher order nonlinear interactions between the attributes without the problem of having too many parameters to learn. Let's see the prediction formula in factorization machines. The difference with the higher order linear regression is that the weights WPP prime are not actual parameters to learn, but are rather computed by the inner product of two latent feature vectors, one for P and one for P prime. Okay, so how many parameters are there to learn? For each feature P, there is a weight term WP. Also, there is a latent vector VP of dimensionality K. So in total, the number of parameters to learn is only linear in the number of given features. This makes training of factorization machines possible. We said that factorization machines are a generalization of matrix factorization. Let's try to explain this relationship. Let's assume that only the item and user attributes are kept. That is the blue and red columns. In this case, factorization machines are equivalent to matrix factorization with a baseline estimate. Let's see why. On the top is the prediction formula for factorization machines. There are three components: a zero-order term in green, a first order in yellow, and a second order in blue. On the bottom is the prediction formula for matrix factorization with baselines. There are again three components: green, yellow, blue. The two green components are clearly equivalent. To see the equivalence in the yellow components, observe that at the top formula, only one user and one item are active. So the sum is actually two terms, the weight of the user and the weight of the item. These two terms correspond to the user and item bias terms in matrix factorization. To see the equivalence in the blue components, observe again that only one user and one item are active. So the product XP times XP prime gives 1 for the target user and item. In that case, the sum has only one term, which is equal to the weight WP P prime. This weight is given by the inner product of the latent vector for the user and the latent vector for the item. This inner product is exactly the inner product computed in the matrix factorization formula. When the factorization machine has more attributes to work with, it becomes more expressive than standard matrix factorization. In this slide, we show a relationship between factorization machine and the SVD++ model. This time the features available are the user ID and item ID, as before, blue and red columns, but additionally we have the features describing the other movies rated by the user, the orange columns. Remember that these orange columns have a value of 1 for the movies that the target user has rated. To make our point the relationship to SVD++, we hereafter assume that instead of putting a value of 1, we put a value of 1 over the square root of number of movies rated. This is a form of normalization similar to that used in SVD++. Okay, so let's see again the prediction formula for factorization machine at the top. At the bottom, we see the rating prediction of SVD++. Again, there is a relationship between components of the same color. This time, factorization machine is not equivalent to SVD++, as it contains some additional terms. However, the point to make is that some of the terms in the top formula are exactly those contained in the SVD++ formula. Let's see this. The green components are clearly equivalent. The yellow component at the top has two summands that are equivalent to those in bottom yellow. It also has some other terms not shown here. For the blue component at the top, focus on the interaction of the movie attributes with the attributes of the user and of other movies rated. Then, if you look closely, you should see the equivalence of these terms to the blue component in SVD++. Factorization machines are a flexible model that can easily include additional sources of information. In some sense, matrix factorization can have the same functionality. One drawback of factorization machines is that they can be a bit rigid. They always consider all pairwise interactions, even though some of these interactions might not make sense. In the previous example, we show a factorization machine that has the same terms as SVD++, but also some additional terms. These terms might actually hurt prediction accuracy. Next, we discuss a model-based variant of item-to-item collaborative filtering. It is called Sparse Linear Method, or SLIM. Remember the prediction formula we had for the item-to-item neighborhood approach. We predict a rating deviation for the target user and target item using rating deviations of similar items that the target user has rated in the past. The past rated similar items are those in the neighborhood n of I given u in this formula. The prediction computes a weighted average. Remember how these weights are computed. Weight Wij is the similarity between item I and j based on the ratings these items get from other users. It can be computed, for example, using the cosine similarity. But what if, instead of computing the weights, we learn them? The weights now become the parameters in a model-based approach. So, we will see how to apply this idea. First, however, we simplify the prediction formula. One thing we do is to remove the neighborhood and instead consider all items. Also, we will not be predicting deviations, but simply predict ratings. The last simplification we do is assume that weights are normalized to sum to 1. We end up with a very simple formula as shown here. The target rating is the weighted average of all other ratings given by the target user. Note that because the weights sum to 1, we don't need a denominator to normalize the weights. In matrix form, the predicted rating matrix can be represented as the product of the ratings matrix and a weight matrix W. Here we assume that all missing ratings are set to 0. In the case of explicit feedback, that is ratings, this is the case when we mean center the ratings. Let's put the matrix prediction formula into pictures. The predicted ratings R hat depends on the weight matrix W that has shape n by n, the number of items. You may think of W as containing item-to-item similarities. As we said before, these similarities will be learned instead of computed by a predefined formula. The number of parameters is quite large in this model, and this is a problem. What we would like is to have to learn far fewer weights, only the important weights. To enforce this requirement, we can include in the cost function a regularization term that penalizes a dense matrix W, or equivalently promotes a sparse matrix W with few non-zero weights. This regularization is based on the sum of absolute weights, and it is called L1 regularization. In contrast, when talking about matrix factorization, we did not care about sparseness in the latent feature matrices, so we used L2 regularization, the sum of squared weights. So, to summarize, the machine learning task in SLIM is to find the sparse matrix W so that the predicted ratings R hat is close to the known ratings R. Do you notice one main difference with matrix factorization? Are users being modeled in SLIM? No. The model only cares for item-to-item relationships as captured in the weight matrix W. What does that mean when we want to recommend to a new user? Well, we can immediately recommend to the new user without learning again the model. We can add a new row in the R matrix and compute the product with W to get the predictions for the new user. Notice that we can keep the matrix W as is. We do not need to learn its parameters again. Compare this to the matrix factorization case, where we need to first learn the latent feature for the new user before making any recommendations. So, how many parameters does the SLIM model have? There are n squared parameters in W, where n is the number of items. There are probably not enough ratings to learn that many parameters, even if we enforce the sparseness constraints. There is enough. So let's see what has changed with the factorized W matrix. The predicted ratings R hat is equal to the product of R with Q transpose and product with Y. Does this look familiar? Well, compare it with SVD++. We will now review a few neural network approaches for collaborative filtering. First is a technique based on restricted Boltzmann machines. This was actually the first neural network approach that appeared during the Netflix Prize competition. So we will gently introduce restricted Boltzmann machines, or RBMs, which are stochastic neural networks used for generative learning. They are quite simple. They have a layer called visible that acts as both the input and the output layer. They also have a single hidden layer that has stochastic binary units. This means that one such unit takes only a 0 or 1 value, which is decided by some probability. Connecting the visible and the hidden layer are connections with weights and biases. These weights and biases encode the input into the internal binary representation. In the opposite direction, they also decode a binary representation into an output. The learning process in RBMs, that is to learn the weights and bias terms, is called contrastive divergence and is quite different from backpropagation or gradient descent used in regular neural networks. Let's see how RBMs can be used for collaborative filtering. The input to an RBM is user-based, meaning that it is a series of ratings for a particular user. Each rating is represented as a vector of length 5, where each entry represents a star. The number of input units in the visible layer is equal to the number of items. As we see in the figure, a user has rated some items. For example, for the first item, the user gave 3 stars, hence the filled box in the first input unit. For some items, the user did not have a rating, so no box is filled. So, the input is a sparse binary representation of the user's rating. This is then transformed into a dense binary representation in the hidden layer. In turn, that dense binary representation is converted into an output where the boxes now contain probabilities for star ratings. To make a prediction, these probabilities are sampled. There are a few issues with RBMs. As you may have noticed, they can only handle integer or discrete ratings. There must be as many boxes per input, per item, as possible ratings. Here we had 5 boxes. Another issue is that predictions can be expensive, as the output probabilities must be sampled to predict ratings. For these reasons, they are no longer considered relevant methods for predicting ratings. A popular technique to predict ratings is based on simple autoencoders. They are shallow, feed-forward neural networks that are trained with backpropagation and are used for unsupervised learning. In the simplest case, they have a single hidden layer, an input and an output layer. The hidden layer contains far fewer units than the input layer and encodes the input into a dense representation called embedding. This representation is similar in principle to the latent feature representation of matrix factorization. On the other end, the output layer has exactly as many units as the input and essentially decodes the embedding back into the original sparse space. There are weights and bias terms that connect the layers to each other. When training an autoencoder, the goal is to learn weights such that the output matches the input. Let's see in more detail how autoencoders work. We have the following parameters. The weights are organized into 2 matrices, W superscript 1 for the connections of the first layer, the input to the second layer, the hidden layer. W superscript 2 are the weights connecting the second to the third layer, the output. Similarly, we have biases organized into 2 vectors, B superscript 1 and B superscript 2. X denotes the inputs, x hat the outputs, and a superscript 2 the values in the hidden layer. Let's see how we get the values of the hidden and output layers, a superscript 2 and x hat respectively. At a unit in the hidden layer, first all inputs are weighted by a row of the matrix W superscript 1. Then they are summed and a bias term is added. Finally, some nonlinear activation function is applied. This can be the sigmoid function or the rectified linear unit ReLU, for example. The values of the hidden layer are similarly weighted by the W superscript 2 matrix, summed, and passed through another nonlinear function to produce the output x hat. As said before, the learning objective is to have x hat, the output, be similar to x, the input. The hidden layer contains a dense compact representation, the embedding of the inputs. Let's now see how autoencoders apply to collaborative filtering. The simplest way to apply them is to learn a representation, the embeddings of items. We call this scenario the item-based input because the input is all we know about an item. That is, the ratings from all users of the specific item. In other words, it is a column of the ratings matrix. The input is depicted in the bottom of the figure, the input layer. This layer has m units, 1 per user. Here we show as shaded a unit if the corresponding user has rated the item. Next, the hidden layer contains k units and thus produces an embedding of dimensionality k for each item. The output layer has again m units, 1 per user. Again shaded are the units that correspond to ratings. The training objective is to make the output similar to the input, but with a twist. We do not care about the non-shaded output. Why? Simply because we don't know these ratings. Okay, so how does rating prediction work? Suppose we have finished the training, we now want to predict the rating of a target item to a target user. We input the known ratings for the target item, and at the output, we look at the non-shaded unit that corresponds to the target user, and that is the predicted rating. In a similar manner, one could have used a user-based input to obtain embeddings for the users. This time, the input is a row of the ratings matrix. In another work, an autoencoder variant called denoising autoencoder is used. The difference is that this type of autoencoders try to learn a more robust representation of the input. It does so by seeing a slightly corrupted version of the input, where some noise is added. And then it tries to decode the original uncorrupted input. In the context of recommenders, collaborative denoising autoencoders, or CDAE, are introduced to learn embeddings of users. This means that the input is user-based, that is, all ratings or clicks in the case of implicit feedback for all items. This is the green part of the input layer. In addition, the target user is one hot encoded, shown in the yellow part. A hidden layer of k units holds the target user's embedding, which is then decoded into the predicted clicks of the target user. Rating prediction is done as in plain autoencoders. In general, neural network approaches are more generic, meaning that they have more expressive power than matrix factorization, at least in its basic form. To see this, let us try and implement the matrix factorization model as a neural network. The idea is to use a shallow neural network with one hidden layer. Moreover, all activations are linear. For ease of presentation, we ignore all bias terms from the model. The input layer contains 1 unit per item. The input is always a single item, one hot encoded. The hidden layer contains k units, which correspond to the latent dimensionality, the number of factors used to represent users and items, k. We use q to denote the weights of the first layer. At the hidden layer, we get z, which is the product of q with the one hot encoded item x. Then the output layer contains 1 unit per user. The weights of the second layer are denoted as p transpose. So the output y is the product of p transpose with z. If we look at a particular output unit corresponding to user u, we see that the output is the dot product of the ith column of q with the uth column of p. And this is exactly the matrix factorization model. So weight matrix Q contains the embeddings of the items, and weight matrix P the embeddings of the user. To make sure you have understood how this neural network operates, convince yourself that the hidden layer units contain the embedding of the item I, which is one hot encoded in the input of the network. In the last part of these slides, we will see the changes we have to do to use matrix factorization when we only have implicit feedback. The ideas also apply to other model-based collaborative filtering approaches. Okay. Here we focus on binary implicit feedback, where a user has either interacted or not with an item. So the ratings matrix contains only ones and all other entries are missing. Let us see what is the challenge with such data. How do you train a matrix factorization model? Well, you have two options. Option 1 is to ignore the missing ratings, just as we did in standard matrix factorization for explicit feedback. Okay, but what is the problem here? What does the model learn to predict if all it sees are ones? Of course, it should learn to predict just once for the missing ratings. And this is not what we want, because simply we cannot distinguish the good from the bad items. Option 2 is to not ignore the missing ratings, and instead treat them all as negative feedback, zeros. Then we learn from all ratings. This seems like a better option in that the model does get to see ones and zeros. But think of what a perfect model would learn. Here perfect means that it has the capacity to overfit the training data. So this perfect model will learn to predict 1 to known ratings and 0 to missing ratings. Again, this is not what we want because we cannot distinguish the good from the bad items. Let me note here that in practice, there will be some form of regularization. So in the end, we will not end up with a perfect model, and not all missing ratings will be 0 in option 2 or 1 in option 1. But this is just the effect of non-perfect training. It means that the learning task is not well defined. So let's see how we can address this problem. Among the two options, the second seems to be the only way to go. Let's try to directly address its shortcoming. We should avoid learning to predict just zeros for the missing ratings and ones for the observed ratings. There are some small changes necessary to the matrix factorization idea. Basically, there are two different methods for this task: weighted matrix factorization and Bayesian personalized rating, which we will discuss next. First is weighted matrix factorization. The key idea is to assign confidence from the ratings we see. First, how confident are we that when we see a 1, it means a positive feedback, that is, the user actually likes the item? Well, not much. As we have argued, for example, a user might buy or click on an item and not like it, in which case the feedback is actually negative. Or actually like it, in which case the feedback is truly positive. Similarly, how confident are we that a 0 means a negative feedback? Again, not much. The user might not buy or click on an item because they are simply not aware of that item, in which case the feedback can be either positive or negative, or because they are aware of the item and chose consciously not to buy or click the item, in which case the feedback is negative. These questions were not well posed. Here are some better questions to ask. When can we increase our confidence that 1 is a positive feedback? Well, this can happen in the case where we have non-binary feedback. For example, when the implicit feedback is the number of times a song is played. The higher the number, the more likely the feedback to be positive. This can also happen when we have other external sources of information. For example, we somehow know that the user in this demographic is probably interested in this item. Okay, so when can we increase our confidence that a 0 is a negative feedback? This can happen if we know that the item was viewed by the user but not actually clicked. For example, if we log the recommendations made, we can identify the items that were skipped. Another way is we assume that certain popular items are well known, so that the user ignoring them probably means they do not like them. As before, other external sources of information can also increase our confidence. But here are some possible definitions of confidence weights that we encounter in literature. First, for observed feedback, let's assume we have non-binary feedback like counts. For example, the number of views of an item. This is captured by the variable CUI and concerns rating RUI. One way to define confidence weight is by setting WUI, the weight, equal to 1 plus a scaled version of CUI. When the count increases, so does our confidence that this feedback is positive, and the rate of increase is controlled by a parameter alpha. For missing feedback, assume that we know the overall popularity of items. Let Fi denote the popularity of item I. This can be collected by statistics across all user interactions, for example. Now we can set weight WUI according to this formula, where W is a fixed term and exponent A controls the impact of popularity. If an item is very popular and we have missing feedback for it, then this means that we should be more confident that this feedback is negative. Let's now see how weighted matrix factorization works. The important thing to notice is that the prediction formula remains the same as in the case of explicit feedback. Here we ignore the bias terms, or equivalently we roll them into the latent features. This means that the learning task still has to learn the same parameters in the matrices P and Q, which have the exact same function. What difference is the optimization goal? The cost now is given by the formula shown here. Two important changes should be noted. First, the confidence weights directly multiply the squared error. The second change is that we consider all feedback, not only the observed feedback, as in standard MF. This is why the sum here is over all user item pairs. Let's see the first change in more detail. How do the weights affect the learning? When our confidence in one feedback is high, we assign higher importance to its error term. If the prediction is bad for a confident feedback, then it is even worse now. When our confidence in one feedback is low, we assign lower importance to its error term. If the prediction is bad for a feedback we are not confident in, then this is more tolerable now. A last issue to discuss is the learning algorithm. This can be simply stochastic gradient descent as before, or it can be alternating least squares ALS. In the latter case, there are some performance tricks that one can apply to make ALS more efficient. The second approach to handling implicit feedback is a Bayesian approach. The main idea of this approach is to compare pairs of items. It operates based on an assumption. An item that is rated by a user is preferred over a non-rated item. Put differently, observed feedback is considered stronger than missing feedback. Let's see what this translates into. Consider a pair of items I and J. If both are rated, then there is no preference expressed. This means that we cannot tell if users prefer I to J or the other way around. If both items are not rated, then again there is no preference expressed. We still cannot tell which item among the two the user prefers. However, if only one item is rated, say I, then based on our assumption, we claim that I is preferred over J. So our assumption means that we only learn about preferences between an item that was rated and an item that was not rated. So our training examples are item pairs for each user, or equivalently, they are triples U, I, J, where for user U, item I is preferred over J. And the training goal is to learn a function that will predict 1 for such triples and of course 0 for the other triples. Specifically, we want to learn a score x hat of uij that captures the preference probability that item I is preferred over j for user u. We want to constrain this score to be a probability, that is, take values in the interval 0 to 1. So we apply the logistic function shown in the figure that has exactly this property. If x hat is low, then the probability will come out close to 0. If x hat is high, the probability will come out close to 1. So we have this x hat score capturing the preference relationship between I and j for user u. But how do we compute it? What are the parameters to learn? One way to compute x hat is to use a model, say matrix factorization, to predict the rating of items I and j for user u and repurpose these predictions. We can use the formula shown here where from the predicted rating of item I, we subtract the predicted rating of item j. Let's see why this makes sense. If item I is preferred over j, we want to learn to predict a rating for I higher than that of item j. This way, their difference is positive, and so is xuij. The bigger the difference, the closer to 1 the probability then becomes. In contrast, if item j is preferred over I, we want to learn a rating for j higher than that of I. This way, their difference is negative. This time, the bigger the absolute difference, the closer to 0 the probability becomes. Okay, so we have seen how to handle the training examples, these triples. But how many are there? Well, for each rated item I by a user u, there are too many unrated items j. Given that users rate very few items, this means that there are around n squared possible positive, negative, rated, unrated, or observed missing pairs of items per user, where n is the number of items. This is clearly too much. We cannot have that many training examples. To make this more clear, remember the case of matrix factorization with explicit feedback. There, we had as many examples as the number of observed feedback, the number of non-missing entries in the ratings matrix. In the case of weighted matrix factorization for implicit feedback, we have one example per user item pair. This means n times m training examples, which is much more than the number of observed feedback. Here, in the BPR method, we have n squared times m, which is an even higher number. So clearly we must do something about it, and the solution is to reduce the number of examples per user. What we do is for each rated item, we sample only a few of the unrated items to create far fewer pairs. Typically, we may choose 5 or 10 unrated items for each rated item. This dramatically reduces the number of training examples. And in the end, we need to learn over the created training examples we have selected. The model parameters come from the underlying model, for example, matrix factorization. What we have changed is the training examples and the cost function, which now needs to measure how accurate our preference probability estimates are. As a final note, we can identify two learning approaches. The first is called point-wise learning, as in the case of weighted matrix factorization, where the focus is on making accurate rating predictions. As a result, we say we optimize for prediction accuracy. The second learning is called pairwise learning, as in the case of BPR. The focus is to be able to distinguish the relative preference between two items. This means we optimize for ranking accuracy to be able to tell which item should rank higher than the other. This means that this type of learning is more suitable for top-N recommendations, where we want to create a short list of N recommendations to present to the user. And this is actually the scenario we meet most often in practice.